All right, let's get into it. We have all seen these absolutely stunning images that come out of an MRI machine, right? They show us the hidden world inside our own bodies. But have you ever stopped to think, how in the world does that actually work? How does a machine listen to your body and somehow turn that into a picture? Well, today we're going to go on that journey and find out.
I mean, just look at this thing. This is a slice of a human brain, and the detail is just incredible. You can see all the different tissues, the intricate folds, and all of this is captured without a single cut. It's like having a superpower, a window looking directly into our own biology.
And that is the million-dollar question. This is not a camera snapping a photo. The MRI machine isn't seeing this image in the way we do. It is building it, constructing it from a totally different kind of information. So how does it go from hearing these tiny, faint signals to creating, well, this? To get our heads around that, we've got to start small, like really small, atom-level small. See, the secret to MRI isn't some dye or tracer they inject into you. It's the very stuff that we're all made of.
It really all begins with water. Our bodies are mostly water, which means we are just jam-packed with hydrogen atoms. And at the very heart of every single one of those hydrogen atoms is a proton. Now, I want you to think of these protons as billions and billions of little tiny spinning magnets.
So here's the first big step. On the left, that's what's happening in your body right now. All those tiny proton magnets are just pointing in totally random directions. They're all canceling each other out. But the moment you slide into the super powerful magnetic field of an MRI scaler, bam, they all snap to attention, aligning with that field just like a billion compass needles all suddenly pointing north. Okay, so all our little proton compasses are pointing north. Now what? The scanner sends in a quick pulse of radio waves. It's just the right frequency to knock those aligned protons sideways. As they get knocked over, they start to wobble, kind of like a spinning top that's been bumped. And that wobble gives off a tiny radio signal of its own. That's the resonance part of magnetic resonance imaging.
And this is a perfect illustration of that exact moment. The big magnetic field is pointing straight up. Then that yellow RF pulse comes in, and it literally tips the combined magnetic force of all those protons over on its side. It's that tipped-over, wobbling energy that the MRI's receivers can actually pick up and hear. This is the raw signal that starts it all.
So, the machine has a signal. Great. But a single signal from the whole body, that's not an image. To turn that raw noise into a picture, we have to travel to a really weird but amazing place. A concept that is the absolute core of how MRI works. It's called K-space.
Let's be super clear about this. K-space is not a picture of your brain. It's more like a grid, an abstract map made of raw data. And each point on this map doesn't represent a spot in your body, it represents a spatial frequency, which is just a fancy way of saying it holds information about the patterns of light and dark that will eventually make up the final image. K-space is the blueprint.
Just look at this comparison right here. On the left, that's the beautiful, clear image of the brain we actually want to see. And on the right, that's its K-space. It looks like a weird burst of static, right? But believe it or not, every single piece of information needed to create the image on the left is hiding inside that data map on the right.
I absolutely love this quote from the source material because it totally reframes the whole process. It turns all this complicated physics into an adventure. So instead of thinking about collecting data, imagine you are a pilot, and your mission is to fly a specific path through this strange glowing K-space landscape. Your job is to take a reading at very specific points to chart the entire terrain.
So, what is this map actually telling us? Well, it's not random at all. The very center of K-space, where the signal is the brightest, that part holds all the low-frequency information. This is your broad shapes, the overall contrast between different kinds of tissue, and the outer edges of K-space, that's where you find the high-frequency stuff, the sharp edges, the fine lines, all the tiny details.
And to make this a little more real, check this out. A single data point in K-space, just one reading from our map, doesn't correspond to a single dot in the brain. No, it corresponds to a simple wave pattern, like these repeating stripes that stretches across the entire image.
And, as you see here, a different point in K-space just corresponds to a different pattern. Maybe the stripes are closer together, or they're tilted at a different angle. The final MRI image we see is simply the sum of thousands and thousands of these simple patterns all added together.
So, okay, we get what the landscape looks like. But how does the scanner actually fly through it? How does it chart that path to build the complete map?
This is our main idea, our central metaphor. The MRI scan itself, all those loud clanks and bangs you hear when you're in the machine, that is literally the sound of the machine executing a very carefully planned flight path through K-space. It's stopping at thousands of different coordinates to take a reading of the signal strength at each and every point.
So what's the steering wheel on this flight? Well, that's the job of the gradient fields. These are smaller magnetic fields that the machine can turn on and off incredibly fast. By controlling these gradients, the scanner can steer to any specific coordinate it wants on that K-space map to take its reading. They're the thrusters and the steering wheel of our little spaceship. And you know what? There isn't just one flight path. Technicians can actually choose different strategies for charting the map. They can go line by line, like reading a book. They can go from the center outwards, like the spokes on a wheel. Or they can start at the center and spiral outwards. Each path has its own pros and cons, depending on what the doctors are trying to see. But this journey isn't always a smooth flight. The biggest enemy, the #1 challenge, is noise, just random electronic static. To get a good, clean reading at each point on our map, the signal coming from those little protons has to be way stronger than all that background noise.
And this is exactly what happens when you lose that fight. With a low signal-to-noise ratio, the signal is completely buried. It's lost. Your K-space map is just garbage, static, and the resulting image is, well, it's meaningless. All that information is completely gone.
But when you have a high signal-to-noise ratio, the signal soars way above all that static. Our readings are clean, they're accurate, the K-space map contains really precise information, and when it gets translated, you get a final image that is beautifully sharp and full of detail. So, the journey is over. The flight was a success, the K-space map is completely filled in. The last step is pure math. The computer takes this abstract blueprint of wave patterns and, using this brilliant piece of math called an inverse Fourier transform, it basically develops all that data into the final anatomical image that we can actually understand.
But you know, the journey for the technology itself is far from over. This is what's so exciting. Right now, researchers are using artificial intelligence, like this framework you see here, to teach the MRI scanner how to find the best possible flight path through K-space all on its own. The goal is to chart that map way faster and more efficiently, which could lead to quicker scans and even clearer images.
And that just leaves us with a really fascinating thought to chew on. For decades, we humans have been designing these flight paths based on our knowledge of physics. But now we're asking the machines themselves to discover new, more intelligent routes. What new secrets will they uncover as they learn to chart the incredible, complex map of the human body?